Hello! Today's video is going to be on capacitor charge, current, and voltage. I'm going to expand on my last video about capacitance by getting into the details of how charge, current, and voltage interact with each other. Let's start with this picture of a parallel plate capacitor. So like I talked about in the last video, the parallel plate capacitor is composed of two conductors separated by an insulating dielectric. To kick off this example, let's assume there's already current flowing through the capacitor. And as we know, in metal, current consists of the flow of electrons. So, if current flows downward as I've drawn it, then electrons are really moving upward. Remember, the convention for the direction of current flow follows the movement of a supposed positive charge. This means electrons actually flow opposite the direction of our label currents. Needlessly confusing, I know. Anyway, as the electrons move upward, they have nowhere to go other than to collect on the bottom plate. This is because, as I explained in the last video, a capacitor is two conductors separated by an insulator. No current, electrons, actually flow through it because the insulator has essentially zero conductivity. You could also think of it as having effectively infinite resistivity. Now, just because the electrons can't actually make it to the upper plate doesn't mean they don't exert any influence. As we know from electromagnetic field theory, charges exert forces over a distance on other charges via their electric fields. So what happens is the electrons generate a field that passes through the dielectric, forcing electrons to leave the upper plate at the same rate they arrive on the lower plate. And one quick thing I should include in case you don't remember is that I've drawn these lines in the direction of the electric field, and it's just convention that electric field lines point towards electrons. Really what these lines indicate is the direction that a positive charge would move through this field. So the force vector that another electron would experience is actually the opposite direction of these arrows, which is why the electrons leave the top plate. Anyway, from the outside world, it really does look like current is flowing through the capacitor, even though the conductive circuit is broken by the high resistance dielectric. One consequence of having electrons collect on the bottom plate is that the charge on that plate is becoming more and more negative. And at the same time, electrons are leaving the top plate, causing its net charge to become more and more positive. This charge differential is what causes a voltage to appear across the plates. The positive terminal of the voltage corresponding to the positively charged plate, and vice versa. We say that the charge accumulated on the bottom plate is stored in the capacitor, although the net charge is still zero because it's balanced by the positive plate. But it makes perfect sense that the charge storage would produce a voltage, because voltage is a potential energy density. The more charge crammed into the same capacitance, the greater the voltage that will appear. In fact, the charge stored on an ideal capacitor is related to its voltage exactly as follows. The charge Q in unit coulombs is equal to the capacitance C in unit farads times the voltage V in unit volts. This is exactly why I said voltage is a potential energy density. It shows us that we can think of the unit of capacitance, farads, as coulombs per volt. And we can look at the unit of potential energy density, voltage, as coulombs per farad. As a side note, it just so happens that 1 farad is an absurdly large capacitance. And in most applications, we deal with values in the nanofarad to femtofarad range. In other words, roughly 10 to the minus 9 to 10 to the minus 15. Okay, now I'm finally going to relate the current and voltage in our capacitor. Recall from one of my first videos that current is defined as the time rate of charge, or rather the rate of change of charge in time. I equals dq dt. We also conveniently have a formula for capacitor charge as a function of its voltage, which is going to turn out to be the perfect bridge between the two. So by plugging this into this formula and taking a quick derivative, we have that I equals C times dV dt. In other words, the current through a capacitor is equal to its capacitance times the time rate of voltage, or the derivative of the voltage with respect to time. And this is a pretty crazy result. The intuition we gain from this derivative relationship is that current will only flow through a capacitor if its voltage is changing. Essentially, if you try to apply DC voltage in currents, capacitors look like open circuits. And I encourage you to think about the implications of that for a second. It means we only care to think about capacitors if our circuits involve AC signals. As far as a DC circuit is concerned, capacitors may as well not even exist. Okay, and the last thing I'm going to include in this video is an inversion of this formula to instead express capacitor voltage as a function of its current. And yes, it is as simple as integrating what we already have, but you have to remember to include a constant voltage to represent the initial condition on the circuit. The resulting voltage will be a function of both a change in current over time and an initial voltage. Now for simplicity, we usually wind up saying that this initial time t0 is just 0, but I've kept it in here for generality. And also you'll often see voltages and currents for capacitors written as V of t and I of t to indicate their functions of time, but I've just happened to leave that out here. Alright, so I hope this was helpful, and in the next video I'll continue to expand on capacitors. Anyways, thanks for watching and have a great day.